Hello everyone, and welcome back to another video of Total Organic Chemistry. This time, we'll be moving on from our discussion of Sn2 reactions and their properties to talking about Sn1 reactions, which are just another mechanism of performing the same nucleophilic substitution, but with different sorts of properties and a mechanism, like I said. So by the end of this video, the questions that you should be able to answer are: how does an Sn1 reaction occur? So what is the mechanism? And how is the mechanism different from an Sn2 substitution? And finally, what affects the rate of an Sn1 reaction? So what are the properties? What different criteria affect that rate of reaction? And if you need some review on general nucleophilic substitution reactions, or if you want to brush up on your Sn2 reactions as well, please feel free to subscribe to my channel and take a look at all of those previous videos that I've uploaded on those topics. So let's start with a pretty simple reaction here. We're going to take T-butyl bromide, so with this very large tert-butyl group, and let's say we'll just put this in our reaction vessel with a whole bunch of water. So say water is the solvent in this reaction. And from this reaction, we're going to get a pretty good yield of tert-butyl alcohol, so just substituting that bromine for a hydroxyl group. And if you're pretty comfortable with your Sn2 mechanisms and properties, you should know that this would be an absolutely terrible Sn2 reaction. It would basically not occur. We have so many things wrong with it. We have a very sterically hindered substrate, so that T-butyl group is tertiary. It's going to be a terrible electrophile. And we have first of all, a polar protic solvent, so protic solvents like water are not really favored in Sn2 reactions. And furthermore, our nucleophile, which is also water, is a very poor nucleophile, so it would really not follow an Sn2 kinetics. However, it turns out that, like I said, this reaction is pretty good, so that must mean it's following a different pathway, and that pathway is what Sn1 is. So very similarly to Sn2, Sn1 reactions stand for nucleophilic substitution unimolecular. So this time, the rate law will be first order, and we'll see why that is in a second here. So if we draw out the mechanism here for an Sn1 reaction, we start with the bromine leaving group, first just coming off of the substrate. So we just have that bond breaking, the bromine leaves, and it leaves us with a tertiary carbocation here. So carbon is actually losing one of those bonds to form a lone positive charge on that central carbon. And we know that nucleophiles have lone pairs that they're willing to donate to positive charges. That's where the name nucleophile comes from, positive charge loving. So that water molecule with its lone pairs on oxygen will come and attack the carbocation, forming this adduct here where the oxygen is now bonded to that central carbon, and the oxygen has two hydrogens on it, and it will carry a positive formal charge because it has 3 bonds instead of the normal 2 for oxygen. So oxygen doesn't really like to have that positive formal charge, so the last step here will be another water molecule coming to take off one of those hydrogens from the oxygen, forming our final product, which is tert-butyl alcohol, and a hydronium ion H3O+. So like I said, Sn1 reactions follow a first order rate law. Well, why is that? Well, we know our rate laws are dependent on the rate determining step of our reaction, and it turns out the slowest step, so the rate determining step in Sn1 reactions, is the breaking of the bond to the leaving group. So this first step, where the bromine leaves the substrate, will be the rate determining step, and that only involves one molecule, so that's why we call it unimolecular. So if we were to write our rate law here, we would write the rate is equal to a rate constant K times just the concentration of the tert-butyl bromide. Which means, if you notice, that the rate of the reaction does not depend on the concentration of the nucleophile, which is something that will be very important in Sn1 reactions. So the rate only depends on the concentration of the electrophile, or of the alkyl halide. So let's draw out another mechanism here. We'll start with this alkyl halide here, and if I draw it out with the bromine coming out towards us and the hydrogen on this carbon going into the page, we'll see that this is a stereocenter. And we'll assume for this reaction that we have an enantiomerically pure starting material. So we have all of this one enantiomer and not a racemic mixture. So, like we just talked about, in our Sn1 reaction, the first step is always the leaving group leaving. So this bromine will come off of the carbon to leave us with this carbocation here, adjacent to this benzene ring. And one of the very important things to notice about these carbocations is that they are planar. So we have one substituent, which is the phenyl ring, one methyl substituent, and this one hydrogen going up, and they are all in the same plane, much like radical species if you remember my previous video on radical halogenations. And because this carbocation is planar, that means the nucleophile is able to attack from either side. So what we have is we can have this water molecule here, and let's draw two arrows, one for each direction. So let's say the red arrow here is attacking from the front side, so on the same side of the paper as we are, and the blue arrow will be the water attacking from the back side of the carbocation. So that gives us actually two products here. So we'll have the red arrow again, being with the water molecule coming towards us, so coming out of the page. And again, we'll have that OH2 group with a plus charge on the oxygen. And then very similarly, with the blue arrow, the water molecule is pointing into the page away from us. And after losing that one proton, so I'm not going to draw out that mechanism here, but you know that that proton can just leave. It's usually being pulled off by another water molecule. We end up with actually a racemic mixture of these two enantiomers. So even though we started out with an enantiomerically pure starting material, after this Sn1 reaction, because of the planar carbocation, we end up with a racemic mixture of two enantiomers. We call that racemization, whereas with Sn2 reactions, remember, we get Walden inversion or inversion of stereochemistry. So now let's talk about some of the properties of Sn1 reactions. And one of those properties, like I said before, was that the concentration of the nucleophile and the strength of the nucleophile do not affect the rate of reaction. So even if you have a strong nucleophile and a weak nucleophile attacking the same alkyl halide, they will not have different rates of reaction because remember, the rate of reaction in any chemical reaction is determined by the rate determining step. And with Sn1 reactions, that slowest rate determining step is that first step where the leaving group leaves the substrate, and that has nothing to do with the nucleophile in the reaction. However, what that does mean is that the strength of the leaving group, or the leaving group ability, does affect the rate of the reaction, just like Sn2 reactions. So the weaker base, so the better leaving group, will always increase the rate of the reaction. Another consequence of the unimolecular rate determining step is that sterics have no influence on the rate of reaction either. So whereas with Sn2 reactions, more steric hindrance led to slower reactions because they were sort of clashing with that nucleophile as it approaches the electrophile, that doesn't matter in Sn1 reactions. What does matter is the stability of the carbocation that is produced after that first step. So a more stable carbocation will be more likely to form in the first place, which will make that rate determining step much faster and increase the overall rate of the reaction. And again, if you remember from my video on radical halogenation, the trend of carbocation stability is exactly the same as the trend for radical stability. And the reasoning is the same as well. Hyperconjugation increases the stability of carbocations, so the inductive donating of electron density from substituents of that carbocation will sort of cancel out the positive charge and increase the stability of our final carbocation. So what that means is that more substituents give a more stable carbocation. So we have that methyl carbocations are the least stable, followed by primary, secondary, and tertiary carbocations are the most stable. So this may seem familiar. This is actually the opposite order of reactivity from Sn2 reactions. So with Sn1 reactions, tertiary alkyl halides react the fastest, followed by secondary alkyl halides, which react more slowly, but they still do. And primary alkyl halides usually do not follow Sn1 kinetics, and neither do methyl alkyl halides because the carbocations are too high in energy to form. The last thing that we talked about, remember about Sn2 reactions, was the identity of the solvent. So we know that in Sn2 reactions, polar aprotic solvents allowed for a faster reaction rate because they allowed the nucleophile to still maintain its nucleophilicity without being trapped by those solvent molecules. For Sn1 reactions, we actually prefer polar protic solvents, so solvents that have acidic protons or protons that can hydrogen bond with the transition state in the Sn1 reaction. So if I draw the transition state of the rate determining step here, we have our carbon center, and maybe we can draw 3 different R substituents on that carbon. And then we'll draw a partially breaking bond to the leaving group, and we'll just call that X. So remember, in Sn1 reactions, this transition state does not include the nucleophile at all, only the leaving group. And we know that these leaving groups are usually more electronegative than carbon, so we have a partial negative charge on the leaving group, and we'll have a partial positive charge on the carbon. So because of this separation of charges, a polar protic solvent is actually able to hydrogen bond to the transition state and stabilize it much more than a polar aprotic solvent would. And so that lowers the energy of the transition state and allows for a faster reaction. I hope this video was a good introduction to the Sn1 mechanism and kinetics, as well as the properties of the Sn1 mechanism compared to Sn2 reactions. So thank you again for watching Total Organic Chemistry. Please be sure to like this video and subscribe to my channel. And also, please consider donating to my Patreon. I will link that in the description. And it allows me to continue creating content like this and other related content for you to help you learn.